So in the today's lab experiment, we will be demonstrating the single phase AC voltage control experiment. So the single phase AC voltage controller experiment, the circuit diagram is shown here. This experiment we can perform either using the thyristors, two thyristors, or using a track also. So in either case, we can able to control the AC voltage applied to the load. The simple circuit shown here in this case, starting from the AC supply. This is AC supply, single phase AC supply. In the experiment, we will be doing 2 or 3 different voltage settings. So the supply voltage is in this case 220 volts, 50 edge AC supply, and this AC supply is given to auto transformer. So the auto transformer output side knob is there. By changing this knob, we can able to adjust the voltage impressed to the circuit. So one terminal is connected via a meter to measure the current. Then we have the track or two thyristors which are connected in anti-parallel fashion. Then we are connecting a load. This is a load, and for demonstration here we are connecting a resistive load rheostat, and return is again terminated on the auto transformer. Now see, this is a simple series circuit, and we are trying to control the voltage applied to the load. So this voltage applied to the load need not be sinusoidal, because we have introduced the track or two thyristors which are connected anti-parallel in series with the supply. So depending on the firing angle alpha, the load voltage waveform may be load voltage waveform should be different from the impressed voltage, that is AC voltage. So the purpose of using these two track or two thyristors is essentially to control the RMS voltage applied to the load, so that the power supplied or power delivered to the load is going to be controlled. So as you are aware of that the track or AC voltage controller or two thyristors which are connected in anti-parallel, one of the this thyristor will always operate only in the forward positive half cycle. Then T2 will be operating in the negative half cycle, and T1 is goes to off state naturally at 180 degrees, whereas T2 will go to off state at 360 degrees. But the firing angle alpha from 0 to any value 180, between 0 and 180, we can able to adjust to firing angle of thyristor T1, whereas the firing angle for the thyristor T2 will be in the adjusted in the second half, that is negative half cycle. So the firing angle for the T2 will be 180 plus alpha, whereas the T1 it is right from 0 any value between 0 and 180 degrees. So here I have not shown the firing circuit. The firing pulses should be given to two thyristors with 180 degrees phase shift all the time, because thyristor T1 has to conduct only in the positive half cycle, and firing angle must vary between 0 and 180, whereas T2 has to conduct only negative half cycle, and its firing angle should be in the range of 180 to 360 range. So the firing circuit is not shown here, and the purpose of firing circuit is essentially to give the firing pulses to the thyristors T1 and T2, such that the load is going to get the desired RMS value of voltage. Now I will be showing the different components used in this experiment. We start from the AC supply. AC supply is connected to the auto transformer. The auto transformer terminals are this, and by varying the auto transformer knob, we can able to vary the output voltage. For example, initially I am setting the voltage. Right now, if you look at the voltage which is displayed at the top left corner, is roughly 8 volts are there. Now I am adjusting this voltage 8 volts supply voltage to 60 volts. So the voltage now you can see at this point, this is 59.2 volts. Okay, and below is the current waveform in the circuit, and the below waveform, current waveform is not sinusoidal, and there is a firing angle is there, and this current will follow the voltage because the load is resistive load in this case. Now this is the unit which is internally we have the two thyristors which are connected in anti-parallel, and firing angle adjustment circuit is also present. Here this knob is meant for adjusting the firing angle. Okay, so by adjusting this one we are varying the firing angle, and this unit is connected in series with the circuit. So this is a starting point of the circuit, and it is going to AC voltage controller unit, and this is going to load, and load is coming to again back to the AC supply unit. So this is very simple AC series circuit, and if you look at the waveforms on the scope, the first one is channel 4 is a pink trace which is AC supply voltage applied to the series circuit through a triac, and this is the voltage appearing across the load. So at this moment the firing angle is close to 45 degrees or little over than the 45 degrees, and if you take the AC supply voltage, it is 58 supply. Cycle time is one cycle time is 20 milliseconds, and half cycle time is 10 milliseconds. So here the firing angle we can adjust anywhere between 0 and 10 milliseconds. So if you are computing the firing angle, we will tell the what is the firing angle equivalent time we are going to tell, and you people have to transform this time into firing angle alpha using the formula 10 milliseconds is equal to 180 degrees. Okay, so if I mention 1 millisecond firing angle means it is equal to firing angle equal to 18 degrees. Okay, so accordingly you have to take the alpha, and by using the standard formulations you can able to compute RMS average voltage and power factor, all other factors, RMS voltage, and what is the displacement power factor, and what is the harmonic spectrum of this distorted voltage waveform as well as the current waveform. We will be giving readings, so you can able to match these readings through analytical formulas. Since it is a resistive circuit, the voltage impressed across load is shown here. This is yellow trace, and current is also similar shape. Only thing is the magnitude will be different. So both load voltage, load current waveform is identical, but if you look at the source voltage, which is AC voltage is not going to be changed. It is fixed by utility. So load voltage is only going to change if I change the alpha. So now I'm just to adjust the firing angle and show you how the load voltage is going to reduce. So at this moment the firing angle is close to 45 degrees. Now I will change the firing angle more than 90 degrees. So you can see that firing angle is now more than 90 degrees because it is close to 150 degrees alpha. Firing angle is close to 120 degrees now. So if you look at the yellow trace is load voltage. It is an alternating waveform but not strict sinusoidal. But if you compute the RMS value, the RMS voltage impressed to the load is going to be very low. So by adjusting the alpha, we can change the voltage impressed to the load such that the power demand supplied to the load will be changing. So in view of this one, this particular experiment we will call it as AC voltage controller. Is essentially controlling the AC voltage impressed to the load. We will call it as AC voltage controller. So during the experimentation, we will be setting two different input AC voltages, and we give the observations pertaining to the RMS value of fundamental component, different harmonics, power factor at the input terminals, okay, other aspects. So your job is taking these samples using the analytical formulations. You have to validate for each and every firing angle, and also you have to compute the different harmonics.
Now note down the readings. Firstly, we set the input voltage to 60 volts, so it is approximately 59.6 volts. Then we will note down the firing angle. It is in millisecond. You have to convert into degree. It is 2.9 millisecond. Next, input current is 227.9 milliampere. Next, power is 12.5 watts. Reactive power is 13.5 volt ampere. Power factor is 0.92. DPF is 0.97. Now, THD is 31.3%. First harmonics is 214.6 milliampere. Third harmonics is 51.3 milliampere. Fifth harmonics is 32.7 milliampere. And seventh harmonics is 18.4 milliampere. Now, we will change the firing angle and takes the reading. Various is 4.2 milliseconds. Input voltage is again 60 volts. Input current is 205.8 milliampere. Power is 10.2 watts. Reactive power is 12.3 volt ampere. Power factor is 0.83. DPF is 0.92. THD is 43.3%. First harmonics is 184.5 milliampere. Third harmonics is 72.3 milliampere. Fifth harmonics is 30.7 milliampere. Seventh is 18.7 milliampere. Now again we will change the firing angle and takes the reading to 5.3 millisecond. Again input voltage is 60 volts. Input current is 157.5 milliampere. Power is 6.5 watt. Reactive power is 9.8 volt ampere. Power factor is 0.66. DPF is 0.8. First THD is 58.8%. First harmonics is 127.2 milliampere. Third harmonics 77.6 milliampere. Fifth harmonic 27.2 milliampere, and seventh 24.7 milliampere. We will set the firing angle 5.9 millisecond. Input current is 110.3 milliampere. Power is 3.2 watt. Reactive power is 6.7 volt ampere. Power factor is 0.46. DPF is 0.75. THD is 64.6%. First harmonic 106.4 milliampere. Third harmonic 73.6 milliampere. Fifth harmonic 30.5 milliampere. Seventh harmonic 20.5 milliampere. Now we will again set the firing angle and takes the reading to 6.5 millisecond. Input power is 60 volt. Input current is 109.5 milliampere. Power is 2.6 watt. Reactive power is 6 volt ampere. Power factor is 0.42. DPF is 0.63. THD is 72.7%. First harmonic 69.3 milliampere. Third harmonic 50.6 milliampere. Fifth harmonic 34.4 milliampere. Seventh harmonic 17.5 milliampere. Now we will set the input voltage to 120 volt and again varying the firing angle and takes the various reading. We will set the firing angle 2.1 milliseconds. Input current is 495.3 milliampere. Power is 58 watt. Reactive power is 59.4 volt ampere. Power factor is 0.98. DPF is 0.99. THD is 18.5%. First harmonic 486.4 milliampere. Third harmonic 54.9 milliampere. Fifth harmonic 47.4 milliampere and seventh harmonic 38.3 milliampere. Now again we will change the firing angle to 4.1 millisecond. Input current is 430.3 milliampere. Power is 44.9 watt. Reactive power is 53 volt ampere. Power factor is 0.85. DPF is 0.93. PhD is 40.9%. First harmonic is 391, 388.8 milliampere. Third harmonic is 132.9 milliampere. Fifth harmonic is 64 milliampere. Seventh harmonic is 37, 40.9 milliampere. Now we will set the firing angle to 3.4 millisecond. Input current is 0.472 ampere, that is 472 milliampere. Power is 5.3 watt, 53 watt. And reactive power is 57 volt ampere. Power factor is 0.91. DPF is 0.96. THD is 32.1%. First harmonic 443 milliampere. Third harmonic 110 milliampere. Fifth harmonic 0.069 ampere. Seventh harmonic 0.037 ampere. Now set the firing angle and 5.1 millisecond. Input current is 0.347 ampere. Power is 27 watt. Reactive power is 41 volt ampere. Power factor is 0.65. DPF is 0.8. THD is 59.3%. First harmonic is 0.262 ampere. Third harmonic is 0.160 ampere. Fifth harmonic is 0.057 ampere. Seventh harmonic is 0.052 ampere. Now we will set a firing angle to 6.2 milliseconds. Input current is 317 milliampere. Power is 24.5 watt. Reactive power is 38.8 volt ampere. Power factor is 0.62. DPF is 0.77. THD is 62.4%. First harmonic is 230 milliampere. Third harmonic is 152 milliampere. Fifth harmonic is 61.6 milliampere. And seventh harmonic is 45.3 milliampere. हेलो हेलो मेरी आवाज आ रही है क्या हेलो
Yes, ma'am.
डू यू हैव एनी क्वेश्चंस हेलो you people have any question otherwise I will leave the meeting Okay, we are done with the class. Thank you.